Math is, of course, central in physics. Subjects like calculus and linear algebra form both the language that physical theories are written in, and they provide us with a lot of tools for solving physics problems. But one mathematical subject that you probably don't associate with physics is number theory. On the surface, this study of integers and their factorization should have nothing to do with the motions of objects. However, because of the quantum nature of physical reality, there are situations where number theory provides incredible insight into a physical system. This video will consider the quantum system of the particle in a box. In this setup, a particle is free to roam around the inside of a box but can never leave it. However, we want to consider a light particle like an electron, which is behaving quantum mechanically. In quantum mechanics, particles are described as waves, which encode the probability of finding a particle around a given position. So instead of a billiard ball bouncing within the walls, you should imagine a wave, which can take on non-zero values in the box, but is zero everywhere outside the box. We will consider two variants of this setup. The first variant is the 1D box, where a particle is free to move on a finite length line segment. Once again, we describe the particle as a wave that assigns a value to every position in the box. But the thing about a quantum system like this is that even though the wave function evolves over time, we only need to know the states that have a certain energy. The evolving states will have an energy that's indeterminate. It's in a superposition of different energy levels. But we only care about the actual definite energy states that form a spectrum. And then if we can understand that spectrum, we can fully understand this system. For this 1D box, there's an analogy of these states to a plucked string. When you pluck the string of an instrument, like a guitar, it vibrates as a wave. This wave can be deconstructed into the sum of a fundamental wave, which has the frequency of the note you are playing, and overtones, which are waves with integer multiples of the fundamental frequency. The states for the 1D box are a lot like this. All of the states have an integer multiple of the frequency of the lowest energy state. The integer multiple associated with any state is a number which I will denote n. Then we have a formula where we can get the energy of any state in terms of n. The energy is just given as n squared. Since n is strictly a positive integer, it is clear that there is only one state corresponding to each energy, and only positive perfect squares are allowed for the energy levels. Now it's time to move on to the second variant of our system, which is going to be the main focus of this video. It is the two-dimensional box, where a particle is free to move within a square. We are once again wanting the states that this system can be in that have definite energy. Because of the nature of this system and the mathematics of quantum mechanics, the states that are allowed for the two-dimensional box are products of two of the states allowed for the one-dimensional box. The new states look something like this. You can think about these states as waves resonating in two dimensions with independent harmonics. Therefore, there are two numbers that uniquely identify any state for the 2D box. I will call these m and n. And just like last time, each can be a positive integer. In the two-dimensional box, the energy is given as E equals m squared plus n squared. Whereas in the 1D case, each energy had a unique state. It is clear that there are often more than one states of the two-dimensional case associated with any particular energy. For instance, if m and n are different integers, they can be swapped to produce a distinct state with the same energy. This concept is called degeneracy. The degeneracy is the number of states with a certain energy. So for example, for the energy of 5, the degeneracy of that energy is 2, because there are 2 states associated with it. However, the degeneracy of the energy 2 is only 1. This concept of degeneracy is extremely important in physics because it determines the probability that a quantum system will be at that energy. Therefore, degeneracy needs to be known to determine the statistical and thermodynamic properties of the system. However, for the two-dimensional box, It's currently unclear whether an energy level can have more than two states associated with it, or even how we can predict the degeneracy of an energy without just using brute force. Furthermore, it is difficult to say which energies should be allowed at all. This is where we can introduce the two fundamental problems that this video aims to solve. Which energies is the particle in the two-dimensional box allowed to have, and how can we find the degeneracy of a particular energy? We can observe from the energy formula that a particular energy is allowed if it is an integer and if that integer can be represented as the sum of two squares of positive integers. This is where the connection to number theory begins. We can even rewrite the energy formula in a way that links the problem to lattices. First, observe that every state of the two-dimensional box system can be uniquely identified with a pair of positive integers. Therefore, we can visualize each state as corresponding to an intersection point on the two-dimensional grid. So, the pair of numbers for each state is a unique vector in this lattice. Since the energy is equal to m squared plus n squared, this energy is actually something called the norm of the vector. The norm is just the square of the vector, or its magnitude squared. You might now recognize our problem of finding how many states have a particular energy as being almost equivalent to the problem of counting how many vectors in this two-dimensional lattice have a certain norm. So suppose we're trying to figure out how many states have an energy of k. Well, this is equivalent to figuring out how many vectors in the upper right have a norm of k. And we can do this by first taking all of the vectors in the lattice that have that norm, and then we subtract the number of vectors which live on the axes with that norm, and we almost have our solution, but then we need to divide by 4 to get rid of the vectors that are in the wrong quadrant. We can break this into a couple of cases though. Notice that the only way that there's going to be vectors on the axes with a norm of k is if k is a perfect square. And if k is a perfect square, then there will be 4 vectors on the axes that have that norm. So we would subtract 4, but then in the end we divide by 4. So to find our number of states, we just have to take a fourth of the number of vectors in the lattice that have the right norm, and if k is a perfect square, then we subtract by 1. And if k is not a perfect square, then we don't have to subtract by anything. Already, we have done something fairly impressive by restating our essential problem for our quantum system as a number theory problem. Now, if we know how many vectors in the lattice have a particular norm, we can find out how many states of the two-dimensional box have the energy we're interested in. This is truly incredible because now all we have to do is solve this number theory problem, and as it turns out, this problem is extremely well studied. The solution to this problem uses a special type of function from number theory called the Dirichlet character mod 4. In this video, I'm going to call the function that we'll use chi. Chi only takes integers as input, and it outputs either 0, 1, or -1. The reason why chi is called a Dirichlet character mod 4 is because it outputs values only according to its input's congruence mod 4. If you don't know what this means, an integer is either congruent to 0, 1, 2, or 3 mod 4, according to what the remainder is when dividing the integer by 4. That is, a number is either a multiple of 4, 1 more than a multiple of 4, 2 more than a multiple of 4, or 3 more than a multiple of 4, respectively. In this way, all the integers can be cyclically categorized by their congruence mod 4. Our function chi outputs 1 if its input is congruent to 1 mod 4. It outputs -1 if its input is congruent to 3 mod 4. And it outputs 0 if its input is even. This seems like a strange function to introduce, but there's a really important result in number theory that's going to help us solve our problem. As it turns out, there's a way to find out how many vectors have a norm of k using this function chi. All we have to do is figure out the divisors of k, and then take the character of each one of those and add them together. The number of vectors of the norm k is 4 times that sum. But remember, to find the number of states, we end up having to divide by 4. And so we don't even need to multiply by 4 in our case. We just need to sum up chi for all of the divisors. And then once again, we subtract 1 if k is a perfect square. If we're trying to figure out how many states have an energy of 50, we first need to find all of the divisors of 50. The divisors of 50 are 1, 2, 5, 10, 25, and 50. The number of states with this energy is just the sum of chi for all of these divisors, since 50 is not a perfect square. Calculating these characters, we have that chi of 1, chi of 5, and chi of 25 equal 1 because all of these numbers are congruent to 1 mod 4. They're all 1 more than a multiple of 4. And chi of 2, chi of 10, and chi of 50 equals 0, because all of these numbers are even. So summing these terms up, we get that the number of states with an energy 50 is 3. With this, we found our first energy which has more than 2 states associated with it. On the lattice, this corresponds to the fact that the vectors 7, 1, 5, 5, and 1, 7 all have a norm of 50, because the square of their magnitude is 50. So we've answered a lingering question. Is it possible to have more than 2 states at the same energy? Yes, it is, and we've shown it by factoring a number and adding its Dirichlet characters together. Let's look at another example. Take an energy like 9. This number is square, so we'll have to take that sum of chi minus 1. So the number of states is chi of 1 plus chi of 3 plus chi of 9 minus 1. Chi of 1 is equal to 1 as we showed earlier. Chi of 3 is equal to negative 1 because 3 is 3 more than a multiple of 4. And chi of 9 is equal to 1 because it's 1 more than 8, a multiple of 4. The total number of states is then 1 minus 1 plus 1 minus 1 is equal to 0. These results are absolutely marvelous to me. If you have done any physics, it seems absurd that we solved a physics problem by factoring a number and finding the modular congruences of its divisors. Yet, spectacularly, it works for finding the degeneracy. This formula will also lead us to another astonishing result about which energies are allowed. We can reformulate our sum over divisors so that it's a product. We do this by noting that every divisor of a number is a part of that number's prime factorization. Take the number 50, for instance. It has the prime factorization 2 times 5 squared. Any divisor of 50 can be formed by taking a power of 2 that divides 50 and a power of 5 that divides 50. So to construct any divisor, you choose either 1 or 2, and either 1, 5, or 5 squared, and then multiply those factors together. As you can see, each choice generates a divisor of 50. This holds for any number, and it can be leveraged for our problem. The reason is that our function chi is multiplicative, meaning that chi of a times b is equal to chi of a times chi of b. For instance, chi of 15 is equal to chi of 3 times chi of 5. So we can decompose chi of any number into a product of chi of all of its prime factors. These two ideas can combine to give us the sum of chi of the divisors of a number. Take the number 50 again. Similarly to how we constructed the divisors of 50, we can construct chi of any divisor of 50 by taking chi of a power of 2 and chi of a power of 5. Once again, we generate chi of all of the divisors uniquely this way. Since we are interested in the sum of these values of chi, we can write that sum as this product. Why is this helpful? Because now we know that this sum of divisors is 0, if and only if one of these factors is 0. Then we can consider cases and see when this happens. The easiest case is when we have an even prime number, so the number 2. In this case, the first term of the factor is chi of 1, which is equal to 1, but every other term is chi of an even number, so all of these terms are 0. That means that if the number we're checking is even, the factor for the prime 2 is always going to be 1. Another case is when there's a prime factor that is congruent to 1 mod 4. It's not difficult to prove that any power of such a number will also be congruent to 1 mod 4. This basically has to do with the fact that 1 squared is equal to 1, and thus also congruent to 1 mod 4. Therefore, a factor corresponding to such a prime has a 1 for every term. Because these first two cases always result in a positive factor, they will never make our sum of chi for the divisors equal to 0. The last case is when there is a prime factor that is congruent to 3 mod 4. This one is the most interesting because if we square this prime, then its square is congruent to 1 mod 4 because 9 is congruent to 1 mod 4. So here, the terms will alternate between being 1 and negative 1. If we stop on an even power of that prime, this factor will be 1. If we stop on an odd power of that prime, this factor will be 0. What this tells us is that if there's an odd power of a prime congruent to 3 mod 4, then the entire sum of chi for the divisors will go to 0. The caveat is that to count the number of states at an energy, we also need to subtract 1 if our number is a perfect square. So if the number is not a square, we just make sure to check that it has no odd powers of a prime congruent to 3 mod 4. But suppose the number is a perfect square. Then it cannot have odd powers of any prime, so we don't need to worry about the condition that we just stated. But since we are subtracting 1 from the sum of chi, we have to make sure that this sum of chi is greater than 1. That just means that we need a prime that's congruent to 1 mod 4 in our factorization. So we have this flowchart that gives the rule for if any energy is allowed. So let's take a look at a few examples where we can apply this rule. Let's first consider the energy 75. First of all, 75 is not a perfect square. So we just have to figure out if there are any odd factors of a prime congruent to 3 mod 4. 75 factors into 3 times 5 squared. So there is an odd power of a prime congruent to 3 mod 4 because there's an odd power of 3. Because of this, the energy 75 is not allowed. Let's take a look at one more example. Consider the energy 100. 100 is a perfect square. So all we have to do is figure out if it has a prime congruent to 1 mod 4 in its factorization. Because it has the prime factor 5 in its factorization, the energy 100 is allowed. So what we figured out is that if we want to figure out if an energy is allowed or not for the two-dimensional box, then all we have to do is factor that number into its prime factorization and apply our rule. Once again, I just think this is a beautiful application of number theory to quantum mechanics. And it feels so unexpected to me that prime factorization plays such an important part in understanding this quantum system. With these results about which energies are allowed and about how many states exist at each energy, we can calculate pretty much any thermodynamic quantity that you can think of. We can, for instance, calculate the entropy or the average energy of the system at a given temperature. Most importantly, we can construct a function which is called the partition function. It's a function that encodes the probabilities of a system being at any energy. Because of this, a lot of these other quantities, like entropy or average energy, are put in terms of the partition function. The reason why the partition function is so powerful is that it is essentially a generating function of the sequence of the number of states at each energy. That is, it is a generating function of the sequence of degeneracies. And what's amazing about the partition function for the two-dimensional box system is that it can be formulated in terms of a modular form called the Jacobi theta function. In fact, using generating functions and this Jacobi theta function can yield the formula we used for counting vectors on the grid earlier. I hope you can see that the connection between this physics problem and number theory is incredibly deep. This crossover between number theory and physics isn't an isolated phenomenon either. Because confined quantum mechanical systems typically exhibit quantized or discrete energy levels, many problems can be reformulated into problems about integers, sometimes leading to rich number theory. In fact, there is modern research which involves this interaction between quantum mechanics and number theory. For instance, a certain type of quantum field theory on a torus has a partition function that is a very famous modular form studied by Ramanujan. Another example is how ideas from string theory were used in the proof of the monstrous moonshine conjecture, linking the monster group to a modular function called the elliptic J invariant. However, I think the problem in this video is a really beautiful example of how these two fields can intermingle, and I'm really happy that it's so accessible to a wide audience. Thanks for watching.